Cool. So yeah, today we're going to talk a little bit about kind of theoretical bounds on MEV, which is maximal extractable value. I think you've had a couple talks in the seminar before about that. I think last week you had a talk on prof, and I saw a couple other talks. This talk takes a different lens than a lot of other talks. It's sort of focused on some theoretical questions of what are lower bounds to how much MEV can actually be removed, and what are sort of overall sort of like what are the kind of how should you think about the theoretical limits of MEV mitigation. So you know the so one important thing about blockchains is there's sort of this notion of verifiability and unauditability, right? I can verify that my transaction made it into the blockchain. I can also verify that the execution happened in a certain way. And it's also auditable. If there was some type of fraudulent interaction from a provider like a validator or sequencer, I can usually find a way to correct for that. So one question you ask is, where is this uncertainty coming from? And so MEV is sort of inherently tied to uncertainty. So let's kind of look at the sort of transaction flow for blockchain users and where this uncertainty comes from. So first we have the notion of ordering. So reordering transactions can change particular users' payoffs. They can change prices on chain. They can make transactions revert. Inclusion, actually being able to guarantee that your transaction is a temporary monopolist, like a validator or miner, doesn't censor you, is actually very important. Third is atomicity. Without atomicity guarantees, oftentimes there can be financial losses for participants such as liquidity providers and AMMs. And then finally, there's, of course, relaying, where network layer attacks influence sort of where and how cross-chain execution happens. And in Ethereum land, and to some extent Solana, this comes under sort of something that we call proposer builder separation. I think in Solana that's a little bit different, but you have the same types of problems. And finally, there's post-execution uncertainty, which is, what is the value of a user's state if it's reverted due to some type of other action, like a fraud proof that's valid? So each of these.
Can I ask? Can I intervene already?
Yeah.
Sure. Quick question about atomicity. So I can see all the other points you're making concerning uncertainties. Atomicity is a bit puzzling, because blockchain guarantees atomicity of transactions by design. So, and liquidity providers, anybody that cares about atomicity, can hack whatever they want in a single transaction and guarantee atomicity. So what do you mean by uncertainty here?
I guess I mean something akin to the following. So in Solana, if I have multiple DEX pools, say a pool for token A to token B and a pool for token B to token C, if there are transactions that are, and sorry, let's have the third one, pool A to C. So we have the triangle. If there are transactions such that none of those states are locked at the same time, an MEV auction will process all those auctions in parallel separately. However, the auctions in Solana get merged if there's any common state that's touched. So in this case, by trying to do an atomic arbitrage, I'm effectively causing a write lock on two pieces of state. And how that lock gets executed can actually give me uncertainty of the final price, especially if I'm thinking of, like, I have multiple routing paths across this kind of AMM graph.
So this is cross-chain or cross-sub-chain?
No, this is within a single chain, but just like the proposer has some choice of which order they execute the locks in. So it's like the choice of topological sort gives you a different payoff function, right? So your payoff function isn't just, oh, I give you a valid topological sort of your DAG. It's like each sort has a different payoff, and the proposer can influence which sort they choose.
All right. Well, you and I can follow up offline and dig deeper into that. Definitely not the case on a single other chain, whether it's Cosmos chain or Ethereum or anything like that. I'm not sure whether Solana is. So. Anyway, let's take this offline.
Yeah, this has more to do with how parallel execution chains operate, and but yeah, okay. So how do we think about this uncertainty? We have some notion of some functional and some notion of a set of payoffs. Sorry. Um, we have sort of some notion of types of uncertainty, so these different types, and some notion of payoffs, and we want to sort of look at some minimax bound on the worst case payoff. So what is MEV? MEV sort of is a sense in which economic uncertainties are placed on unsophisticated actors by sophisticated actors. So what does that mean? Well, maybe first we need to think about how transactions actually enter a blockchain. So usually users submit transactions to a pending transaction pool, and miners and validators are allowed to choose a few things. So first, inclusion, which transactions are included. So in a sort of honest model, an honest miner or validator sees a transaction with a sufficiently high fee and they include it. However, of course, there's no enforcement of that. And so that's sort of the question of censorship resistance. Generally, as long as there's sufficiently many miners and validators, you'll have eventual inclusion. But if you have a transaction that has a time dependence, you may value inclusion quite differently. Second is ordering. So the order in which the transactions are executed there's a lot of general leeway to the miner or validator, up to some constraints, such as I have a DAG, and the DAG sort of order has to be respected. Second, what we see in practice is strategic users will pay validators for extra protocol guarantees on inclusion and ordering. So here we can think of MEV as any excess value paid to the validator via such agreements. So let's go through some examples. I know that I think it seems like there's been a broad base of topics in the seminar, so I wasn't sure exactly the familiarity with different things, but hopefully I tried to reduce some of the more mathematical constructions. So first, if we consider minor extractable value in constant function market maker, so that's things like Uniswap. What are these things? Well, they're defined by an invariant function, phi. Generally, there's a unique sort of monotone concave representative of this. And this function takes in reserves, so that's an amount of assets. So in this case, an amount of Ethereum and an amount of USDC. And a valid set of reserves are reserves along the curve, so where these red dots are, which represent a certain amount of USDC versus a certain amount of ETH. And the idea is at the points where there is more USDC, USDC is worth less. And we can see that by trying to describe what the prices are that are quoted by CFMM. Geometrically, they're effectively the slopes of the tangent lines at different points. And at the points where there's more USDC, you can see that the slope is higher, effectively saying the price of Ethereum is higher. And this is just a natural way to represent supply and demand. So let's talk about examples of MEV. The first type of MEV, that's sort of the simplest, is front running, where a user places a trade that's marked by 1. They push the price up. As you can see, the slope of the tangent line goes up. And then the user who is submitting a transaction at 2 has to pay a higher price. The second is back running, which is a user does a transaction to push the price up. And so now maybe they hold that asset at that price. And then by back running, I actually lower the price, which causes the assets they're holding in their portfolio to be worth less. And as you can see, you see the slope go up and then go back down. And a natural way to do something that harms a user who is trying to make a normal transaction is to do a sandwich attack. And a sandwich attack is something where I do a front run transaction ahead of a valid user transaction, which is number 2. And then I do a back run transaction. And I get a profit because I push the price up. Then I have the user transaction push the price up more. And then I sell back at that higher price. And there's a natural notion of profit. You might say, hey, this sounds theoretical. This is just a view of the last week's sandwich attacks on Ethereum. So there's around $160,000 that were extracted. So this is a very real, not hypothetical thing. So at the beginning, this paper's title is Towards a Theory of MEV, Part 2. So you might say, what was Part 1? So I think going to Part 1 will help inspire what the set of problems we're looking at in Part 2 is. So Part 1 showed a sort of somewhat counterintuitive result, which is that sandwich attacks aren't always the worst for user utility, user welfare. In some sense, what this means is there's sort of an analog of Brace's paradox, where one user can have a worse outcome. So they might get a worse price than they would have gotten in an averagely ordered block. But the other users get better welfare. And one of the reasons for that is that the sandwich attacked user changes the routing path that the other users' transactions take through a AMM graph. And so they're able to get a better price. So you can think of the sandwich attacker as effectively helping influence routing. This sort of demonstrates that MEV is not always bad from a welfare maximization standpoint. And in a lot of ways, you need to think of it in terms of being diverted to the right uses. So a natural next question is, when is MEV bad? And I put bad in quotations. And a lot of this talk will be about trying to define what it means for it to be bad. So as given in the previous example, the sort of counterintuitive example, if you care about welfare maximization as opposed to perhaps revenue maximization or individual utility maximization, MEV isn't necessarily always bad. But one question is, can we generalize this to beyond just one application, CFMMs, where we can write out explicit formulas and write convex optimization problems and prove their solutions satisfy some bounds? So Part 2 tries to answer this question with regards to ordering. So the first question is, and this is a question that has been asked by many academic papers, is it possible to have a fair ordering given MEV uncertainty? And so we're going to argue via formal arguments to show that there is no fair ordering mechanism that can be a welfare maximizer for all in a particular sense, which sort of says for every fair ordering algorithm, there exists a welfare function, an application effectively, to which it gives a much worse outcome. Okay, and so then the natural question is, if that such a thing doesn't exist universally, can we quantify how unfair an ordering is? And so that's sort of what we'll try to argue, that the kind of proof of when I think about welfare maximization gives a natural way of showing that there is no fair ordering, sort of gives a way of quantifying how unfair a block is.
So I have two questions. I guess one is that how is, like, it's on the quotation mark, but how should we in general think about what fair means here?
We'll talk about that in the next two slides.
Okay, and then I guess a question on the previous slides is when you say MEV could potentially increase, the social welfare, should we think about that as, MEV itself is profiting, and potentially depends on how the routing goes. It may route to different pools than the original route. Is that how we should think about the benefits versus the cost of those cases?
Exactly. Yeah, exactly. Like the sandwich attacker causes a particular pool, which may be so if you've ever seen Brace's paradox, Brace's paradox has this notion of there are four cities and there's a graph that is parallelogram plus the diagonal. And the idea is that the fastest route is the one that actually goes through the diagonal. So it's city A to B to C to D. I'm drawing with my hand, so probably not the most ideal thing, but I would highly recommend understanding what Brace's paradox is first. Kind of it's like a classical economics paradox. And Brace's paradox basically says, hey, if everyone is selfishly optimizing and they all take the same route, they will all actually give themselves worse welfare because they've congested the road. So imagine the latency it takes across each route is dependent on how many people are going on each route. And you can view the AMM functions in the same way. And so we prove that you get a Brace's paradox, and then we prove a price of anarchy result. But yeah, that's more the goal of this talk is to say, hey, can we do this for more than just AMMs?
Mm.
Cool. And so, yeah, I happy to talk more offline. I mean, but about that, if that's all right. Cool. So, and then the final question is how do we bound worst case execution? So, I think there's a lot of different things in practice as opposed to the theoretical papers on fairness that are giving you data on what the execution guarantees are. So, one natural question is how far are they from best or worst case or average case? All right. Well, to your point, a natural question is what is fairness? And there's obviously many definitions, and people fight over it. I think a lot of philosophy is built off of making sure that the definition of fairness is not sort of equal in every context. But the principle we'll take is the maximum payoff received by any individual is not so much greater than the average welfare of every individual. That's sort of the highest level thesis we'll use. And so order fairness protocols, they generally are payoff or economically agnostic, and they can't really guarantee anything about how they impact the payoffs for all users. So these are things like FIFO or first come, first serve execution, or things that try to approximate that. There's also economic mechanisms, which focus on, again, trying to maximize payoffs minus externalities, which are much closer to this. And in practice, if we look at live blockchains right now, almost all ordering protocols are economic mechanisms. Basically, none of the order fairness protocols are used in practice. In sort of like, if I look at sort of the volumes going through them. And you might say, why do we choose this definition? I think I sort of took a classical economics paper on welfare economics and theory of fairness, and then sort of this is sort of a distillation of that for thinking about how to think about whether an economic mechanism is fair. So how do we define this in a blockchain context? So first, we start with a payoff function. So a payoff function is real value function that takes in a sequence of n transactions. The main key thing is that the universe of transactions for this analysis will be initially fixed. So you can think of this function as providing the welfare, so that the sum of utilities effectively, given this set of transactions. Since we're only going to study ordering, we can say this is equivalent algebraically to a payoff that maps a permutation and ordering. So Sn is the symmetric group for a set of permutations to a real number. So this sort of takes an ordering and gives you a welfare. You can think of F as representing the welfare of a whole block. So maybe this is, like Ethereum proposer builder separation where people are bidding on the whole block. Maybe it's a single application. Maybe we're only looking at the transactions that touch a particular call site, or maybe it's something where we're looking at multiple applications. But the key thing is we're kind of trying to make the notion of this payoff function relatively generic. So examples. So the simplest one is the one that is constant across all permutations. So this is a function that's permutation invariant. In a lot of ways, it's perfectly fair. Doesn't matter what order you choose, but very few financial functions satisfy this. Maybe payments do, but anything that has a transaction cost or impact cost, which makes it path dependent on the particular ordering you choose, doesn't have this. So AMMs being the simplest example. And so CFMMs, we have these known concave payoffs to LPs given some trades of size delta 1 to delta n. This payoff is smooth in a particular sense that we'll talk about, but you should really think of the smoothness in terms of continuous math, something like the gradient is smooth or Lipschitz, given enough liquidity. And finally, we have non-smooth payoffs, which are liquidations. So liquidations occur in perpetuals and lending protocols on chain. They are things where in a certain ordering of transactions, so i.e. an Oracle update comes in and then all of a sudden something is liquidatable, whereas if an update doesn't come in, it's not liquidatable. They depend on particular sequences of transactions. And so one natural way to abstract that is to say these non-smooth payoffs are indicator functions over sets of permutations. So this function, this notation one subset sub A says this is a function that is one if the permutation pi is in the set A, which is a subset of permutation. And that's a non-smooth payoff because it has a distinct jump. So let's try to first think about how this looks in pictures and sort of also maybe hopefully to answer Kite's question earlier, get some intuition for what the result in the earlier paper says. So suppose I have a sequence of 7 transactions. So there's 2 up transactions and 3 down transactions. And the x-axis here is the index, so what order they're executed in. So consider permuting the trades. So we pick a permutation P, a permutation pi, and we look at the price under that permutation. So now maybe we went from up, up, down, 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 up, to up, 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 down, down, down. And consider another permutation, maybe one that makes the trades go down, 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 up, 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 up. What we showed in the first paper is given sufficient liquidity in the AMM pool, you can guarantee that the maximum overall permutations of the price divided by the average overall permutations of the price is O of log n, which sort of says the deviation in the worst case reordering from an adversary to the average case is at most log n worse. So this is the sense in which, this is another sense in which, an adversary, even if they can reorder you, you can kind of bound how much worse your loss is. Now a second question is, what happens if I add sandwich attacks? So I sandwich in different places. And so by sandwiching, I might move the price up or down, depending on the direction. And a natural thing that you might expect at the end, which is what we show, is again, given sufficient liquidity, you can sort of bound the maximum price deviation versus the average price deviation in this way. And this says this function f, which is really this price function, like what is the maximum price, what's the price you're getting, is relatively fair, even with sandwiches, in the sense that the max and expectation, you can control how much they deviate multiplicatively. So now let's consider the non-smooth payoff, the liquidation.
Tarun, can you give us some intuition about this log n? There's a big O before it, which I don't know what the constant, how the constant is related to prices. Is it hidden in that constant? Can you give some intuition into this logarithmic bound?
Yeah, so the constant is really dependent on the AMM curve's gradients and Hessian, and really the Hessian. You can think of the constant as basically the condition number of the Hessian of the trading function. because the Hessian of the trading function, which is the invariant phi that I was talking about earlier, controls the sort of a bound on locally, like what the maximum price deviation you will have is. So the constant in front, you can actually explicitly write in terms of the AMM parameters. But really it's about local properties of that invariant function. The log comes from the fact that imagine that I take the sequence of trades and I order them randomly. I can actually generate a sort of tree of the directions that the trades are going in the sense of like as I injected a trade, it goes, is it greater or less than some previous sequence of trades, and sort of you can think of like writing the partial sums of the trades as sort of this kind of tree. And if there's sufficient liquidity, you can show the tree is balanced, which gives you the log n. Now, there are a lot of examples that are known for AMM functions where it's actually O of 1 and not log n. But there are pathological CFMMs where it is log n. So, and the pathological CFMMs come from the condition when the condition number is sort of degenerate.
Maybe I can ask a related question then, because I mean, I guess people are going to grapple a little bit with this notion of fairness as being somewhat arbitrary. I mean, so for example, you could have just as easily taken more like a more Rawlsian approach and looked at the distance of the average from the worst off person as a measure of fairness. And so I imagine this sort of log, getting this log representation is pretty convenient. Is that sort of unique to the definition of fairness, or maybe could you just maybe give us like a little bit further justification about why you define fairness the way you did?
Yeah, that's a good question. So one argument is that a lot of ordering mechanisms that exist in practice generally benchmark to something like I've randomly ordered. In a lot of ways for blockchain functions, it's actually quite hard to solve the max or min in practice, because in general, you have a lot of latency constraints and you have to execute, you can only sample a small number of permutations. The second thing is, if you look at a lot of MEV searchers, the way that they actually try to find their optimum is they do some sort of like approach that looks a bit like doing a Markov chain, sampling a random pi, and then iteratively improving it. And so in some sense, if you're doing something that looks like that the SMT solver style things that start at a random initialization and then gradient search for the max, then the correct benchmark is really how far did you move from your initial search. And so there's a sense in which I'm trying to, this is mapping to like what people do more in practice. You are correct that kind of getting the max versus min would be interesting. I think for CFMMs, you can get a similar style bound if it's sufficiently smooth, the invariant function. So for max versus min. So because again, like the constant in the big O is like the condition number of the curve. So it's like really about the dimensions in which it's scaling the most versus least.
Can I bug you a little more on the log n? What is n here? This is a continuously updating DEX, right? DeFi protocol. It seems like log n or not log n will grow forever.
And here is, we're assuming there's a fixed set of transactions, and we're only looking at the ordering, like the payoff under different orderings.
Right, but it is pretty arbitrary because the boundary between blocks or sets is just completely arbitrary. The AMM will continue updating the price.
Well, that's not
I can just
true, right?
keep.
There's a gas limit. Like there is a sense in which I know an upper bound on n at all times.
So I should think of n as, okay, the amount in which we deviate from a fair price deviation per block is bounded by that block size, but over time it is not.
Yeah, so this is like a single block, effectively.
Okay, but if I decide to look at the same question over 1 minute instead of one block, or 1 hour instead of one block, the log will explode, right? I mean, so I'm really trying to get a sense of what this bound actually tells us.
I mean, it just says within a block where the proposer has the right to reorder arbitrarily, the most damage they can cause you relative to an average ordering is multiplicatively log n, right? So like,
and the larger the block, the more
n.
damage. Okay, and you're saying the larger the block, the more damage they can cause, which is somewhat counterintuitive. Okay.
Yeah, well, there's just more entropy in the trades, right? Like you have to take this worst case over these sequence of trades. So there is some devil in the details of how much liquidity you need in order for this result, which is where the big O comes in.
Okay.
Jerome, I have 2 more questions in the chat. One is that is it possible to relate these bounds to lever? And the second question is there a relationship between the log bound and entropy?
Sorry, Q&A. Sorry, I just opened that. The first question, maybe, so lever is really an average case bound, right? Like an average case over many rounds bound. And, I think some of Siamak's follow-up work on like these, like the auction style stuff is sort of somewhere in the middle. It does take advantage of like, what's the worst case I can deviate within a block. But again, in order to take the continuous limit, they rescale things in a way that this is not doing. So the answer is it's possible to relate it, but you should really think of this as more adding correction terms to that in a minimax sense. And this question about entropy, yeah, again, if you look at the proof there, this is sort of about trying to get a minimax bound over trades that are in some bounded set. So like the trade sizes are between minus M and M, and you look at overall distributions that you can draw for those trades. So it's sort of related, but the main point is that there's a sort of fast mixing time. That's more, instead of thinking in terms of entropy, I would think about it in terms of Markov chains on symmetric group. And this is arguing that this has a relatively fast mixing time. So now that was for a smooth payoff. Now let's consider a not smooth payoff. So this is the liquidation payoff game. You should think of this as how a perpetuals DEX like Jupiter or Hyperliquid works. Also, lending protocols, although lending protocols are generally a lot slower and they smooth the oracles over multiple blocks, stuff like that. So I think this is most close to a perpetuals DEX. So we have an initial price of the AMM, P0. We have 2 N trades in the block, XI, and N of the trades are +1 and N of the trades are -1. Now, given a permutation, we construct a price trajectory. So for instance, although here I seemingly have 2N -1, so imagine there's another red trade here. I'm bad at drawing, I guess. But basically, we have a permutation, and the permutation will permute this price trajectory. So we can have our initial price plus the deviations according to the permutation, and now we get this partial sum set. The liquidation happens if the partial sum ever touches the boundary P0 minus C. So what does this look like? We have a price trajectory given a certain permutation, set of transactions. We permute it, and we get another price trajectory. We permute it, and we get another price trajectory, and this one is liquidated because it touches the boundary. So what you can see here is some sequences of transactions don't touch the boundary, and so then there's no payoff. And some sequences do touch the boundary, and there is a payoff. So there's a payoff of 1 if you touch, and there's a payoff of 0 otherwise. You can think of this Arrow-Debreu security. You can think of this as a barrier binary option. There's a lot of different ways of viewing it. So now suppose that there's only one permutation that touches the boundary. So the idea is that only one of these possible permutations actually is able to go below. This will say that the max over this payoff function is 1, because there's obviously one permutation at which it touches, but the average is 1 over n factorial, because there are n factorial minus 1 permutations that don't touch the boundary. And in this case, this means that ratio that we computed earlier is n factorial. So again, this is a huge gap between the smooth AMM version, where the gap was log n, and for liquidation, it's n factorial. So a natural question is, and this gets to the point of thinking about max versus expectation or max versus min, is how do we generalize this? How do we figure out conditions on these payoff functions, on the welfare function that exists for a block, such that we get bounds? And so we're going to talk a little bit about competitive ratios. I'm going to skip most of the math of how we analyze them, but I'll try to give you some intuition. So hopefully that helps. So competitive ratios. So in this case, the competitive ratio is this max over expectation. Again, there's a lot of practical reasons to consider it, but I do agree that you could consider other measures more price of anarchy like, but for intents and purposes for this talk, we're going to look at this to be defined as lambda f. So one natural question is, the previous example sort of showed some notion of smoothness, how much the function changes as I permute things locally seems to be quite important to bounding this competitive ratio. And so a natural question is, what are those smoothness properties of f that are important for that? And so what we're going to show is we're going to argue that you can use a certain type of Fourier transform and talk about the coefficients and the expansion of the Fourier transform to say whether something is smooth or not. As a note, previous work from me and others showed for an additive competitive ratio, so this is max minus expectation versus max divided by expectation, there's a way in which you can write bounds in terms of the eigenvalues of a graph Laplacian on the symmetric group, but the bounds are too weak. They have lots of square root of n factorials in them, which is still a big number. Okay, so maybe let's start with the intuitive description before we kind of give a little bit more understanding of the math. So we want to demonstrate upper and lower bounds on the competitive ratio as a function of some property of the function. We can think of the roughness, S, as the degree of the Fourier expansion. So imagine we had a way of Fourier expanding this function f, which we'll describe in a few slides. And you can think of S as the largest frequency. So the function is rougher if it has higher frequencies. That's sort of intuitive from sort of the real valued Fourier transform, as well as sort of the Boolean Fourier transform, if you're familiar with that, where I have if I have higher frequencies, my function is bumpier, as in the probability of me moving to a neighbor and it being a different value that's high is high. And so what we first show is we show an upper bound, which is that the competitive ratio is upper bounded by n squared s factorial, where again, s is sort of the number of non-zero terms in the Fourier expansion. Intuitively, what this says is if the function has no high frequencies, sort of it's smooth like an AMM curve, this competitive ratio can be small. The lower bound we show is that the competitive ratio is bounded below by s factorial. So again, this says the highest frequency also gives you a lower bound. We don't show anything about tightness, so it's possible that you could improve the upper bound. But what this effectively shows is that no fair ordering mechanism, so a fair ordering mechanism chooses, you can abstract it to a mechanism that takes in a sequence of transactions, takes in some metadata, and outputs a sequence of orderings or permutations that's allowed. And what this shows is that no fair ordering mechanism can work in a payoff agnostic manner because we have this sort of lower bound. You're always going to distort the function. And a very simple version of this is considering a fair ordering mechanism that returns a set A of valid orderings. And I can always show that the competitive ratio for the indicator function for a function not in A is always n-factorial, kind of like our previous example. So what this kind of gives you is sort of this nice notion of A, smoothness, how smooth the function is, controls this competitive ratio, and B, effectively your ordering mechanism impacts which functions are more easily have a low competitive ratio or high competitive ratio. So there's a bunch of different things that we use in proving this result. We'll kind of ignore some of those and give most intuition. So what's a Fourier transform? So probably most of you already know what Fourier transform is. It's a way of decomposing a complex function into a sum of simple periodic functions. So, in the case of sounds, the simple functions are sinusoidal waves. The high frequency modes are fast moving sinusoids, and the low frequency modes are slow moving sinusoids. And you sort of sum them together to get the real sinusoid. In MEV payoff functions, the simple atom functions are these indicator functions on sets of orderings. The high frequency modes are sort of small constrained sets of orderings, and the low frequency modes are large sets of orderings. And we'll talk about what that looks like. But this is just to give you sort of the analogy if you've seen Fourier transforms before and you want to sort of have something in your brain as a heuristic to think about them with. So the interesting thing about the MEV liquidation game, the thing we talked about where we reordered things, and if it touched, I got a payoff of 1, and otherwise I get 0, is it's sort of a complete set. And what that means is that I can sort of take every function of permutations and I can expand it in terms of indicator functions over sets of permutations. And the point of the Fourier transform is to kind of isolate that, to figure out what the coefficient is for each of these indicator functions. So this is what the intuition you should have is. And in some sense, this says every payoff function can be written as a linear combination of liquidations. So a natural question is, how do we interpret this coefficient f hat? So what f hat really does is it says, what's the sensitivity of the function? Sort of how concentrated is the mass of the function, the welfare function, on some set of orderings? If the size of the set is large and the Fourier coefficient is large, this sort of states that many permutations have a value that's close to the average value. If the size of the set A is small and the coefficient is large, then this says the set contains a lot of values much closer to the maximum. And you can think of sort of some concentration of the values over the different subsets of permutations. So how do we get the upper bounds and lower bounds? So the upper bounds are provided via an uncertainty principle for functions over the symmetric group, or the set of permutations. And the lower bounds are achieved via something called hypercontractivity, which is sort of a way of comparing how smooth a function is in different norms. For economists, this shows up when proving quantitative versions of errors and possibility theorem. We're getting explicit probabilities around what the probability of an arrow failed election is. I will kind of skip a lot of the math on the lower bounds. But the upper bound is actually a lot more intuitive, so we'll talk a little bit about how you prove that. So first, within statistics and information theory, there are a lot of uncertainty principles, not just Heisenberg. There's a bunch of different uncertainty principles, and uncertainty principles sort of say a function and its Fourier transform, they both can't be concentrated in some sense. So generically, there's something of this form where there's a product of a functional of the function itself and a product of the functional of the Fourier transform, and we say it's lower bounded. That functional, for instance, could be entropy, and then this becomes additive. The function could be variance, and then you get the Heisenberg classical uncertainty principle or the Fourier uncertainty principle, where the Fourier uncertainty principle is the one that you learn in school of I take a Gaussian, I take its Fourier transform, the Fourier transform has inverse variance. And effectively, this says a function and its transform cannot both localize the value of this function. So what is the Fourier transform on the symmetric group, on the set of permutations, on the set of orderings? So without going into the algebra, because I think, I'm not sure exactly the audience background, I figured that I would just try to express everything in sort of calculus-like terms, but for the record, I'd say the representation theory and Fourier transform of the symmetric group are one of the most studied things in math. So there's a lot of algebraic structure that I'm ignoring here. So we can think of the basis functions for the Fourier expansion as what are called the set of k juntas, which take a set of k pairs of elements in N that are distinct. And we have an indicator function on the set of permutations which basically says if a permutation pi maps IL to JL for all L, which basically says for each of these pairs, it fixes, say I1 is 1 and J1 is 2 and I2 is 2 and J2 is 1. As long as any permutation does that 2 cycle, the transposition of 1 and 2, this would be 1. So this is an idea of there's k points that have to be fixed by this permutation, and if a permutation fixes those, then it's. And in terms of these unique pairs, you can write the Fourier transform as a sum over the set of all of these pairs. For notational simplicity, I'm not writing out the explicit set. And we expand in terms of these functions. The degree of a function is the maximum k such that there exists a set of pairs such that the Fourier coefficient is non-zero. So this again is, I'm highly oversimplifying. There's a lot more to this, but this is for the purpose of this talk, this is the simplest description. So what is an uncertainty principle for permutations? So theorem, Wigderson, 2021. Let G be a finite group, symmetric group is a finite group, and f from G to R be a function. Then we have this following property, which is a thing that says the L1 norm of the function divided by the L infinity norm of the function, the max of the function, times the L1 norm of the Fourier transform divided by the L infinity norm of the Fourier transform. So there should be a hat there missing. Is greater than or equal to the size of the group. For symmetric group, this actually gives us a direct bound on our competitive ratio. It says 1 over the competitive ratio is greater than or equal to the ratio of the norms of the Fourier transform. What's really nice about this is this tells us how to get an upper bound on our competitive ratio in terms of the Fourier transform. So you could think of this as we have some notion of fairness, like competitive ratio on the left-hand side. And on the right-hand side, we have spectral properties of the function, which is the smoothness of the function, effectively. In other words, this, in terms of uncertainty principles, it also says f and its Fourier transform can both not be fair. Okay, so we'll talk a little bit about the exact bounds. So what's the setup? So one other definition, and we won't have too many more of these. A set of permutations, so again, think of this as a set of orderings of transactions in the blockchain, is T intersecting if for all pairs of permutations in A, there exists some subset of indices such that of size T, such that the two permutations are equal on there. So it says effectively there's sort of a fixed point set of size t that all permutations in NH share. You can think of this in the blockchain context as validators agreeing on a T prefix of a block. So they agree on the first T transactions of the block. They maybe don't agree on the remainder, but they agree on some subset. And our adversarial model is we have a set of algorithms that take an input as input, a set of transactions, T1 to Tn, and they return a T intersecting set of validators. And T will be specified later. But the idea is the adversary sort of has some control over this in how much intersection there is. And you can view the different fair ordering algorithms that we talked about earlier as effectively giving you a different guarantee on what T is. So this is why our results kind of write everything in terms of T intersection. But if you look at all the papers I had earlier, they all kind of give you a different bound on what T is. So let's start with the upper bound. So if we have a set of T intersecting permutations and T is greater than the degree of F, then we get our upper bound, which is of this form. And a very simple sketch of the proof. Uncertainty principle gives the upper bound. Representation theory says given an irreducible representation rho, a set of irreducible representations rho of symmetric group, of which there are many, we can expand the function. The number of irreducibles is indexed by the number of partitions of a set. That's where the something to the square root s comes in. And then we can bound the maximum value representation and then use the union bound to get this. So obviously leaving a lot of details out, but you can read the paper. Lower bound, if we have a T intersecting set of permutations and the degree is less than the minimum of T and n minus T, then we get the lower bound of lambda f is greater than or equal to C times S. Proof, there's a kind of very recent math paper solving a famous conjecture, which says like if I have a T intersecting set of a certain size, then there exists, I can construct, I can find a subset in which all the elements intersect in a certain way. Or actually, sorry, if a set is a certain size, then there's always a T intersecting subset. Then what we do is we can construct a particular Cayley graph whose generating set contains A. We show that the hitting time of a random walk on G upper bounds the expectation of F. And then we bound the hitting time, upper bound the hitting time by the infinity norm and the eigenvalues of the graph. And then we have to use math to get bounds on the eigenvalues, but that will give you a competitive ratio lower bound. So how should we interpret this? First, you can't really achieve optimal order fairness in the sense of a lot of the distributed systems literature for all payoff functions. You really do need the ordering rule to be tied to the Fourier degree. It sort of shows that if your ordering rule is agnostic to the set of welfare functions you're trying to optimize, then there will always exist some welfare function that is worst case. The second thing is you can kind of view this as sort of a Nyquist-Shannon sampling theorem. It sort of says, if my welfare function has a certain degree, a certain complexity, how many samples do I need for the competitive ratio to be small? So again, the main conclusion, economic payoff agnostic fair ordering algorithms do not exist. You can always construct a payoff function with bad competitive ratio. In general, simpler functions have lower MEV and higher user welfare. Simpler in the Fourier degree sense of low degree. With knowledge of the payoff function, there are fairer ordering. So if I know the payoff function, I can construct ordering rules that are fair in the competitive ratio sense for this. And this sort of justifies having application-specific sequencing, because you can think of an application like a CFMM or a Uniswap sort of knows what its payoff function is for its LPs. And so it may say, hey, given this payoff function, I want these sequencing rules. to be used because they have, a low competitive ratio. And you might say, hey, this is all theoretical. How many people in blockchains could tell you what representation theory is? The thing is, people are doing this in practice. If you look at a bunch of different application-specific sequencing protocols, people are moving to this world where the ordering is kind of separated on a per application or per translation unit basis. And some of the reasons for this is effectively to try to lower the amount of MEV that's realized.